All right, so in the previous example, we basically saw that our result in the S domain wound up in a form that was really easy to take the inverse Laplace transform of because it existed as we solved it, right, in the form that we needed it to be in so that we could easily take this inverse Laplace transform from the table. And sometimes that's not going to be the case. And so what do we do if that's not the case? Well, first let's talk about how this particular form of a bunch of sums of terms does tend to make our lives easy. This is due to the linearity property of the Laplace transform. So if I go back to the Laplace transform properties table, I can grab this linearity property and bring it over there with us so we can take a look at it. This is a very important property. I think I already touched on this a little bit, but probably good to talk about it again. So let's throw this in here. So linearity basically states that if I have a sum of all of these terms, or all these different, I guess you could call them terms, I can take the Laplace transform of each term individually, and my total Laplace transform of this entire sum is equal to the sum of the Laplace transforms. That's basically what the linearity property says. So what that means is I could take this function of S, right? It's a sum of three different functions of S, but we're calling it one giant function of S. I could call this f1 of S, I could call this f2 of S, and I can call this f3 of S. And the Laplace transform inverse of this thing, right, is going to give me some function of t, which is going to be equal to the sum of the three inverse Laplace transforms of those individual functions. So I don't have to look at this as a whole giant function with all these terms, right? I can just look at each individual term, take the inverse Laplace transform, and then call it a day. And that new sum of inverse Laplace transforms is the Laplace inverse of my original function. Okay, so all that to say, I can basically just do it one term at a time. So let's keep that linearity property up there, and let's take a look. So the first one here is 4 over s plus 2. So let's just say f1 of s. We want to take the Laplace inverse of that. Okay, f1 of s. That's going to give me f1 of t. And if I look at my Laplace transform table, let me look at that. Actually, let's just go back to it. So it's a 1 over s plus a. It's this type of transform here. So I can take a screenshot of this and bring that over there with us. Sorry, I'm switching back and forth between these slides, but I think it's useful. Let's shrink this down. So this is the one we're going to use here. We can see that it's 4 over s plus 2, so we can say that our f1 of t is going to be 4 times e to the negative 2t u of t. And that's basically my first piece of the puzzle here. I have my f1 of t, right? Now I can do the same thing for f2 of s. So this is, let's just say 1. For 2, we'll just say the Laplace inverse of f2 of s is equal to f2 of t. I'll do f3 in the next video because I think this is getting a little bit long, and I know it's going to be a ton of data, and I have one more page dedicated to this anyways. This is going to be, so it's basically going to be something over s plus something squared. So let's go look back at the table. We've already seen this one a couple times now. So you start to see patterns, right? These start to show up often. So it's this one right here that we've already used. Oops. Let's just grab it. Oh, I could have grabbed it from the other page. I had already copied this. Oh well. So let's go back. Throw that down here. Okay, so we know that it's just going to be 6 times t times e to the minus 5t u of t. And so that's our second piece of the puzzle. We've got our f2 of t, and now all we have to do is find the Laplace transform of this third term here, which right now it's not in perfect form, but we can get it there, and then we can take the Laplace inverse. Forgive me if I'm saying Laplace and Laplace inverse out of order. I think by now you probably know that if we're taking Laplace, we're going from t to s. If we're taking Laplace inverse, we're going from s to t. But I feel myself stumbling a couple times, so forgive me for that. But that's the first two. So we've got f1 of t, we've got f2 of t. Now we just need to get f3 of t, and we'll do that in the next video. Let me box these. I think it's useful for organizational purposes. All right, and we'll see you guys in the next video, and we'll do f3 of t or f3 of s here, and then we'll be done with this example. This is really just me showing how it's easy to use the linearity property if we get something in this form. We haven't even talked about partial fraction expansion yet. Partial fraction expansion is what we need to do to get a function into this form. I'm just showing you why we like this form. So this form makes our lives easy, like I said, and I'm showing that here because we can take each individual function and convert it into the time domain using the table. But we're going to get to the point where we do partial fraction expansion very shortly, which is how we actually get something into this form. Okay, so I'm going to end this video here, and we'll see you guys in the next one.